Earth's atmosphere is an arbitrary boundary. The concept of the Earth's atmosphere having a definitive edge is more of a human convenience than a physical reality. In fluid dynamics and orbital mechanics, the transition from air to space is a gradual thinning of gas particles rather than a hard shell. The problem with a hard boundary. As altitude increases, the density of the atmosphere drops exponentially. However, there is no specific point where the molecules simply stop. Even at altitudes where satellites orbit, there are enough stray hydrogen and helium atoms to create atmospheric drag, which eventually pulls satellites back toward Earth if they aren't boosted. The Kármán line, the 100-kilometer compromise to settle legal and aeronautical disputes. The Kármán line was established at an altitude of 100 kilometers, 62 miles. The logic: at this height, the atmosphere becomes too thin to support aeronautical flight. To generate enough lift to stay aloft, a vehicle would have to travel faster than orbital velocity. Essentially, at 100 kilometers, you cease being an airplane and start being a spacecraft. The debate. Not everyone agrees on this number. NASA and the U.S. Air Force historically used 80 kilometers, 50 miles, as the boundary, granting astronaut wings to pilots who cross that threshold. Physical layers versus arbitrary lines. While we use lines for records and treaties, the atmosphere is better understood through its functional layers. The fuzzy reality. If you define the atmosphere as the region dominated by Earth's gravity and gas, it extends halfway to the Moon. The geocorona, a cloud of hydrogen atoms surrounding Earth, reaches out about 630,000 kilometers. By that definition, the Moon actually orbits inside Earth's extended atmosphere. Ultimately, whether the boundary is 80 kilometers, 100 kilometers, or 10,000 kilometers, depends entirely on whether you are an aerospace engineer, a lawyer, or a cosmologist. Geocorona. The geocorona is the outermost part of Earth's atmosphere, specifically the luminous part of the exosphere. It consists primarily of neutral hydrogen atoms that scatter ultraviolet light from the sun. While we often think of the atmosphere as a thin blue shell, the geocorona proves that Earth's influence extends far deeper into space than most realize. 1. Composition and mechanism. The geocorona is formed when solar radiation, specifically Lyman alpha radiation, hits neutral hydrogen atoms. These atoms absorb the UV photons and re-emit them, creating a faint glow that is invisible to the human eye, but detectable by specialized sensors. Source. The hydrogen comes from the breakdown of methane and water vapor in the lower atmosphere. These light atoms eventually migrate upward, escaping the denser layers. Density. It is incredibly sparse. While it contains millions of atoms per cubic centimeter near the base of the exosphere, that density drops to just a few atoms per cubic centimeter at its furthest reaches. 2. The scale. Beyond the Moon. For decades, it was believed the geocorona ended roughly 100,000 kilometers from Earth. However, data from the SOHO, Solar and Heliospheric Observatory mission revealed that the geocorona is much larger. Radius. It extends up to 630,000 kilometers, roughly 391,000 miles, away from Earth. The lunar connection. Since the Moon orbits at an average distance of 384,400 kilometers, it actually travels directly through the thickest part of Earth's geocorona.